Hi everyone, and welcome to part 6 of my Z80 computer series. In the last video I was adding some RAM to the system. I was doing that on a breadboard just to prototype it to make sure it worked, and as you can see I've now got rid of the breadboard again and I've put the glue logic chips here for the memory decoding. And also the RAM chip is now installed. I think previously this RAM chip was on the breadboard and this was just an empty socket. It's now installed in here. It's all wired up and the logic chips are there. I have actually also, you might have noticed, added some buttons down here. I'm just thinking forward that we'll probably want to be covering input sometime. We've got output on the system with our 7-segment LEDs, but we've got no input to the system. I did ideally want to get 16 of these all the way across the bottom, and I've realised I can't because this lever is going to get in the way. So I'll possibly just put 8 buttons on here, but I'll stick with just the original 4 for now. These are not wired up now, but they'll be there for the future when we want to come to start looking at inputs. So I believe I did promise that this time we would be looking at the concept of the stack and subroutine calls, and it's because of the way subroutine calls use the stack, and the stack requires RAM. We couldn't look at this before until we had the RAM on the system. So let's dive in and take a look at that. So I did think just before we jump into looking at the stack, I haven't really given us a very good overview of the Z80 architecture. So I will do that in the future, but just for now I'll just briefly show you the registers on the Z80. Of course, all of this is in the manual, and that is the best source of information. So if you want to know more info, go and read the manual. But I'll just very quickly go over the registers. So we've got 6 main general purpose registers: B, C, D, E, H and L. We've been using H and L quite a lot, and I think I've used register B and register C a little bit. Not sure, I may have used register D, I can't remember, but all 6 of those are generally considered general purpose registers that are just free for our use. Some of them do carry slightly special purposes, like the HL is often used with addressing. I believe B was used for the DJNZ function for loops as a counter, and C is used for outputting as we've seen. But generally they're considered to be general purpose. There are a couple of other registers there, register A and register F. A is known as the accumulator and generally stores the results of any mathematical operations that we've done, such as addition or subtraction. The results generally go into the A register. And then also the flags register kind of works in conjunction with A, is in that it returns some status flags. It's known as the flags register, register F, and it contains 8. It's an 8-bit register, so there are 8 flags, but I think 2 of them are unused. So if we just look in that in a little bit more detail there, each of these flags carries some kind of purpose to tell us a little bit more information about the results of the operation that was just completed. Can't actually remember all of these. I remember that Z is the 0 flag, so if the operation resulted in 0 in the accumulator, then the 0 flag would be set. There's C is the carry flag. I believe H is the half carry. PV I think is parity / overflow. S is the sign bit if it's a positive or negative number, and I think N is something to do with whether the operation was an addition or a subtraction. But I will look into the flags a little bit more deeply, and we'll probably have a separate video just on the flags. Just at the moment, just trying to make you aware that they're there. There are also an alternate set of these registers. So there's like another copy of them. They're not the same registers, they are just a completely independent set of registers. They're just an additional 8 registers that we can use. You don't have quite as much control over them, but one thing you can do is you can switch these out. That's why I'm showing those arrows showing that you can move backwards and forwards. You can actually swap the contents from one set into the other set. You effectively exchange them, you swap them all over. That can be quite handy if you want to back up all the registers whilst you carry out some operation, and then you can restore them all again a little bit later. So it's just handy to be aware that they're there. And then there are some more special purpose registers. Now some of these are 16-bit registers, and that's why I've shown them as a wide bar, and you can't work with those ones. You can't split them in half and work with one half independently like you could with the registers we looked at so far, such as B and C. You can use that as a single 16-bit register, or you can work on the individual halves B or C independently. You can't do that with some of these 16-bit registers. They are purely 16-bit registers. So we've got PC, that's the program counter. That generally points to the next instruction to be executed. We've got SP is the stack pointer. That's going to be of particular interest to us in this video. You've got registers I and R. They're 8-bit registers. I believe I is the interrupt register and R is the refresh register. Don't think we need to be too concerned with the refresh register because we're not using dynamic RAM. I believe that's what it's used for. Then you've got a couple of indexing registers, IX and IY. Again, we'll get into those into detail in further videos. Probably have one video on each. So this time we're going to be looking at the stack pointer. So we'll have that one covered off, and we've probably talked about the program counter enough. But maybe the IX and IY registers are worthy of their own video, and probably the interrupt register, is worth a look at as well. So let's get into the actual stack. So what is the stack? Well, the stack is a last in, first out LIFO data structure. That is to say, the last item put onto the stack will be the first item taken off the stack. You can think of a stack as a tower of building blocks. As you build up the tower, each block you add sits on top of the last. If you start to take the tower down again, you can only take blocks off from the top of the tower. So you imagine we've got some building blocks here. As we add the blocks, they all stack up on top of each other. And if we start taking them away again, we take them away from the top. So the last one that went on is the first one that comes out. We're going to look at a couple of new instructions that we haven't covered so far. They are the push instruction and the pop instruction. The push instruction puts a value onto the stack, and the pop instruction takes a value off of the stack. So it's that simple. Usually you're pushing the contents of some register onto the stack, and when you're popping them off, you're popping the value off the stack again back into some register that you've specified. So I've got a little example program here just to try and go over the concept of pushing and popping onto and off of the stack. We'll go over this line by line, and as we're doing so, I'll show you a few registers and how these instructions affect those registers. So the registers we're going to be keeping an eye on are BC, DE, PC, the program counter, and SP, the stack pointer. Now the only one we actually know the value of at this point is the program counter. We know that is at address 0000 because that's where we're going to start executing our program. The other registers we don't actually know what's in them, and at this point we don't really care. Then I'm showing you here a section of the RAM. It's actually the very top of the RAM. You can see we've got FFFF. And the values in there at the moment, again, we don't know what's in there. We first switch the system on, we have no idea what contents are in the RAM. So after we've executed the first instruction, which is load SP, FFFF, if we look at the registers, we still don't know what's in BC or DE because we haven't touched those yet. The program counter has incremented by 3, and the reason it's done that is because this is a 3-byte instruction. I've got the bytes over there on the left, so the bytes for this instruction are 31FFFF. so that's 3 bytes. So it's incremented the program counter by 3. And as this instruction was specifically loading the stack pointer with FFFF, we can see that we've got that value now in the stack pointer register. And then I've just tried to show that visually in the RAM, that the stack pointer is pointing to address FFFF. If we execute the next instruction, we can see the program counter increased by 3 again, because it's another 3-byte instruction. We can now see that the BC register has got some contents in it, what we've just written into it. Stack pointer is unaffected. And the next instruction, again, program counter increased by 3. We've now got a value in DE as well. And again, stack pointer not affected. Now the next instruction is push BC. So the registers BC and DE are still the same. The program counter incremented by 1 this time. But the stack pointer decreased by 2. The reason it decreased by 2 is because we pushed a 16-bit number, and 16 bits fits into 2 bytes. And if you look at the RAM, you could see the values. It was the contents of register BC, which I conveniently loaded with BBCC, so it's a little easier to see what was going on. And you can see it's loaded the high byte into memory address FFFE, and the low byte has gone into memory address FFFD. So what actually happens is it decrements the stack pointer by 1 and then puts the high byte into that memory address, and then it decrements it by 1 again and puts the low byte into that memory address. If we execute the next instruction, same things happened again, but this time with a DE register. We can now see the stack pointer has decreased by another 2, and the contents of register DE are now effectively what we call pushed onto the stack. They're now sitting in the memory locations FFFC and FFFB. So what's happening is the stack is growing, but it grows downwards. It's kind of, you kind of have to flip the concept of when we were thinking about the building blocks, the stack was growing upwards. We've just represented this, that the stack is growing downwards. We could have just drawn it the other way and the stack would be growing upwards. I think we do generally refer to the top of the stack as where stack pointer is pointing to. Whether you've visually drawn that upside down or not, it's irrelevant. Still referred to as the top of the stack, even though it's growing downwards in memory. So now we're going to start popping those values back off again. So if I execute the next instruction, which is pop BC, now we see the stack pointer is moving back up again. So it's increased by 2 this time. And the values that we took off the stack were CCDD. Sorry, the values we took off the stack were the values DDEE, because they were the last ones put on, so they're the first ones coming out. And I've actually deliberately popped them back into register BC. So we've actually now, if we look at BC now contains the contents of DDEE. So it contains the contents that were originally in register DE, and that's because I'm popping them off in the same order as I pushed them on. Normally you don't do that. Normally you would pop them off in the reverse order if you want them to go back into the same locations. I've deliberately done this to demonstrate that we can use this technique to exchange 2 registers. So if I execute the last instruction, pop DE, we now see the stack pointer has incremented back to its original position, FFFF, and the values BB and CC got popped off and they went into register DE, so we can see that value in the DE register. And as the program's finished now, you can see the net effect was we actually swapped the values that are in BC and DE. And that's because of the order in which I pushed them on and popped them off the stack. A couple of interesting points to note is that we originally loaded the stack pointer with FFFF, and if you look at the memory contents, that memory location, FFFF, was never touched. We never modified the contents of that. So it's just something to kind of bear in mind, that the location that the stack point is actually pointing to is unaffected. It gets decremented first, and then we start affecting the memory locations. So if you've got something above the stack, because you don't have to put the stack at FFFF, you can put it anywhere you like. If you've got something sitting above it, that first byte there is actually safe. It won't get modified. The second thing to notice is that even though we've taken the items off the stack, the values actually remain in the RAM. There's actually no benefit in taking them out, because if you took them out, what would you put in their place? You could put the value FF in there, or you could put the value 00 in there. But to be honest, it doesn't help. It doesn't benefit anything to take them out of the RAM. So it actually would just waste CPU cycles to try and actually remove them. So they're still there. We just don't consider them anymore. We don't pay attention to them. So that was the stack, and how we push items onto the stack and how we pop items off the stack. And hopefully you'll appreciate from that, you can't use the stack without RAM, because you actually have to be able to write to memory. So we couldn't put the stack pointer pointing somewhere to some ROM, because we just wouldn't write to it. And when we come to pop the values off again, they just wouldn't be there. So RAM is key to using the stack. So with that in mind, let's move on to subroutine calls. So we've got a couple more new instructions here. We've got the call instruction and the ret instruction. The call instruction calls a subroutine by incrementing and pushing the program counter onto the stack, then setting the program counter to the address of a subroutine. The ret instruction returns from the subroutine by popping PC off of the stack. So we'll look at that in a bit more detail, but it is kind of that simple. We just make the subroutine call by pushing the program counter onto the stack, so that when we're finished we can pop it back off again and start executing from there. So you're just storing the return instruction, grabbing it back when you're ready for it. So I've got another example program here, and we'll do the same thing. We'll go through this line by line, and we'll keep an eye on the registers and again the area of memory where the stack is sitting. So the first instruction, same as before, we're just going to load the stack pointer with FFFF. See the program counter has incremented and the stack pointer has been loaded. And I'm just going to load a value into the BC register. Again, program counter got incremented. Now I've executed the call sub instruction. Now what's happened here, if you remember what it said about the call, it said it was going to increment the program counter and then push the value onto the stack. Now what would normally happen with pretty much every instruction, there is one exception that we'll look at the end, most instructions increment the program counter, and they increment the program counter by how many bytes that instruction was. So this is a 3-byte instruction, so the program counter would have been incremented by 3. It was sitting at 006 before we executed this instruction, and it would have got incremented by 3, which would have moved it to 0009. Pretty much every instruction just does that. So then after it's been incremented, then it got pushed onto the stack. And we can see it did get pushed onto the stack because two things. We can see the stack pointer got decremented by 2, as in the previous example program. And we can see the value that actually went onto the stack was indeed 0009. And that is actually our return address for when we want to come back from the subroutine call. Now, the next instruction to be executed is the instruction that's in the program counter, and that's the final bit that the call instruction does. It loads the program counter with the address of the subroutine that we want to call. So the program counter is now loaded with 000A, and we can see that is the first byte of our subroutine. So the next instruction to get executed is this one here, which is push BC. And you can see, we've seen a push instruction before. Stack pointer got decreased by 2, and the values BB and CC, which are the contents of register BC, have indeed got pushed onto the stack, and they're now sitting in the RAM as well. The only reason I've really done that is just to demonstrate to you that you can still use the stack, even though the subroutine return addresses are on the stack. You can still use the stack as normal. You just have to be aware of all of this. So when you're pushing things on and popping things off, just remember that return address is on the stack. It is also a good idea when you're doing subroutine calls to push any registers that you're going to mess about with, push them onto the stack before you start the subroutine call. Then do your work in the subroutine call and mess about with the registers at will. And then when you're finished, pop them back off in the reverse order. They'll all go back into the same registers that they came from. And then when you return, it's kind of just being nice to the calling routine that all the registers are reset back to how they were before you called the subroutine. Because from the perspective of the calling routine, you don't want to be really thinking about, oh, is this subroutine messing with my registers? It's just easier to keep in your mind that a well-written subroutine call won't mess up any of the registers. It will restore them all back. So it's just good practice to push the values before you start the subroutine call and pop them off at the end. You don't have to. If you know what you're doing and you're happy, you don't have to do that. It's just kind of good practice. So I'll execute the next instruction, and I am indeed messing with the BC register here. I've loaded it with FFFF for no particular reason other than to show you that I've modified it. Program counter got increased as normal, and the stack pointer was unaffected. And then we pop BC. We see the stack pointer has increased by 2. The value has been restored back into the BC register. And now finally I'm going to execute this return instruction, this ret. So after we do that, if you remember what it said about the ret instruction, it just pops the program counter off the stack. It's as simple as that. The return instruction is so simple. So the value popped off the stack was 0009. It popped that off and it put it into the program counter. So return is effectively the equivalent instruction as pop PC, pop program counter, but it's just written as return because it makes more sense to us reading the program, making sense of what the program is doing. But it's really just a pop PC. So the return address is now loaded into register PC, and PC always points to the next instruction to be executed. So the next instruction to be executed is indeed the instruction immediately after the subroutine call. So we've successfully completed our subroutine call. Now we've actually executed a halt instruction, and an interesting point about the halt instruction, I did a little bit of reading on it because I wasn't quite sure. The halt instruction is actually one of these instructions that doesn't increase the program counter. The halt instruction effectively just gets executed repeatedly over and over, which means nothing really happens, which is why they've called it a halt. You're effectively stopping the program counter. So you can see that even after I've executed the halt instruction, program counter is still loaded with 0009, so the next instruction to be executed would be this halt instruction again. That's just a side note, nothing really to do with subroutine calls. So hopefully that explains the concept of how a subroutine call works. So just to recap, the call increments the program counter as normal and then pushes it onto the stack, and the return simply pops it back off of the stack. So we'll look at one final example program. I won't go over this in line by line the same as I did before, but what we'll actually do with this one is we'll actually load it onto the real hardware, but I will just talk you through it. I'm just loading the stack pointer with FFFF as we've done in the previous instructions. I'm setting HL to 0000. Then I'm calling this subroutine call, which I've just labelled up as output. Then I increment HL and then loop back to the call again. So I'm just going to repeatedly make this call, but every time I make the call, HL is going to be incremented by 1. And then if we actually look at the subroutine, what that is doing, just pushing BC onto the stack, because I'm going to be messing about with the BC registers. We don't need to do this in this program, but I told you it was good practice, so I thought I'd best do that in this example. Then I'm loading C with 0. Now C is our output port, so this is output port 0. And then I'm loading B with the contents of HL. Remember I said we're going to keep increasing HL. But we're just loading the contents of the memory address that we're pointing to at this particular time into register B. And then I'm going to output the contents of register B onto the port that register C is pointing to. So that'll be port 0, which will be my green LEDs. And then I'm going to do an inc C, and I'm going to do out C, L, and then inc C and out C, H. So the contents of the HL, which is the memory address, will be put onto the red LEDs. Then I just pop BC and return. So let's load this onto the hardware and we can actually see it running. Just before I do that, just to, if it's not obvious, just explain what the program is really doing. It's just dumping our memory contents, pretty much the same as we've been doing before, but I've just rewritten it to make use of a subroutine call. So it should start dumping out these hexadecimal codes here, 31FF, 210000, and such like. It'll just start dumping out our program. The red LEDs will be showing us the memory address, and the green LEDs will be showing us the contents of that memory address. So I'll fire the system up. I say this every time I start it up, I still haven't sorted out the reset circuits, so we'll give it a reset. I'm on automatic clock, so it should run when I release my finger. And there's byte value 31 in memory address 0, FF at memory address 1, FF again at memory address 2, then 21, 00. It seems to be working. These are the correct bytes at the correct memory addresses. So I won't make you wait through all of that because the system is still running fairly slowly, but I'm hoping that that gave you a fairly good overview of how the stack works and how we can actually use the stack to make subroutine calls. So we'll leave this video here. What I'm thinking about doing in the next video is just taking stock, really, just pausing for a second with the development, and we'll probably do just a little bit of talking and thinking about where we're really going with this project, just to refocus on what it is I'm actually intending to build, which is the finished computer. And I just want to talk to you about some of the design decisions that I'm just thinking about at this stage. I'm just wondering which direction to go with a few things. I'm going to tell you what I think, and then maybe you can give me some comments and give me your thoughts. But yeah, we'll leave it here. Thanks for watching. If you haven't done so already, please subscribe to the channel because that really does help me out. And if you liked the video, give it a thumbs up, and we'll see you in the next one.